Hi, everybody. Today we're going to be learning about KSP and some of the typical types of problems you're going to see using KSP. KSP stands for the solubility product, and that's because your K expression is going to look like literally two ions just being multiplied together. That's where the product comes from. So this type of equilibrium is a little bit different than what you've been seeing. It's going to be an equilibrium that's heterogeneous, and what I mean by that is it's going to be between a solid and an aqueous solution. So I just wanted to show you the particle model diagram for how this is occurring.
When solid lead chloride is added to water, a small number of ions are released into solution. Those ions can reattach to the solid, while other ions can dissolve. A state of dynamic equilibrium is reached, in which the concentrations of ions are constant and can be described by an equilibrium constant expression.
So the equilibrium that's going to be established here between ions is going to be, like I said, just a little bit different than you're used to thinking about. Solubility isn't black or white, soluble or insoluble. There's actually a really big spectrum of things that are highly soluble, slightly insoluble. Your book probably lists about 20,000 ways to think of it. So the first problem we're going to do says, consider lead iodide dissolving in water. Calculate the KSP if the solubility is a certain number. So the first thing you have to realize when you're doing these KSP problems is that anytime they give you solubility, what that stands for is a single X term in your ice chart. So solubility is always given as a single X term, no matter how many ions are produced in solution. So I'm going to write down the equilibrium expression I see going on here. So I'm going to have my lead iodide solid in equilibrium with the ions. Lead plus 2, I minus. Looking at this, we're going to have an ice chart. Initial, change, end, or equilibrium. And it looks like my solubility is already given to me. So if I have a certain amount of the lead iodide, I don't really care what it is because it's a solid. It's not going to be in my equilibrium expression anyways. This is going to go down by a certain amount to make my ions. It's going to go up by X here because the relationship here to here is 1 to 1. And it's going to go up by 2X here because it's 1 to 2. At the end, I'll have something minus X here. Again, I don't really care because it's a solid. But my final concentrations of my ions are going to be X and 2X, if you see that. Now, I know my X is equivalent to 0.0013 molar. So let's come up with a KSP expression, products over reactants, and then we can plug in that number. So I'll have PB plus 2, I minus, squared. Remember, you have to raise it to the coefficient. That means I'll have KSP equals, if my X is 0.0013 molar, that'll go there. Now, this is going to be double that. So 0.0026 molar squared. Okay? We solve for our KSP, and then we'll get our answer for that one. And if you look here, we've got the answer for that one, which is 8.8 times 10 to the 9th, okay? So that's how you solve this first problem. And really the hardest part is just knowing what this term, this solubility term means, all right? The next one is only slightly more complicated, but we're gonna take it slow. It says, will a precipitate of calcium hydroxide form when 320 mils of a molar solution of sodium hydroxide mixes with calcium chloride? And they're telling you a KSP. So on the next slide, what I have are the questions that I ask myself when I'm trying to solve one of these problems. These are the questions that I ask myself. I say, okay, if this is a solubility equilibrium problem, what is the precipitate? Okay, well, they tell me it's going to be calcium hydroxide, right? Okay. Where does that come from? Okay, well, if you look, they're mixing sodium hydroxide with calcium chloride, and essentially that's a double replacement reaction. The sodium hydroxide is going to be the contributor of the hydroxide, right, for my calcium hydroxide. Calcium chloride is giving me my calcium. So really what I'm saying is I don't care about the chlorine. not helpful. I don't care about the sodium. Those are all going to be spectators anyway. So they're going to come from NaOH, specifically the OH part, and calcium chloride, specifically the calcium part. Now, what is the equilibrium reaction occurring? Well, they're asking if a precipitate forms. And a precipitate is just the solid in equilibria with the dissolved ions. And so I'm going to have calcium hydroxide in equilibrium, that's in the solid state, with calcium ion and 2 hydroxide ions. The K expression for this is going to be Ksp equals Ca2 plus OH minus, and again I have to square this because there's a 2 in front of it. To solve this problem, what I want to do is, because I don't know if it's going to precipitate, I want to figure out the difference between Qsp and Ksp. So I'm going to use Qsp when I don't know that I'm at equilibrium yet. So if you take a look at my work, here is the expression that I just wrote out right here. And here are the molarities that they gave me in the problem. Now what I'm going to do is I'm going to change all of this to moles because the volumes of my reagents are different. So take this and solve how many moles are in my 400 mils. That's what this is addressing, okay? I end up getting 0.034 moles of calcium. And then this is the total volume of both solutions together, because once I mix them, that's what I have. This one is going to be right here. So I'm going to say, of my 320 mils, how many moles of hydroxide do I have? And then I end up figuring this out here. And then I divide that also by the total volume. To figure out which is greater, Qsp or Ksp, oh, that's helpful. I want to compare the two. So I'm going to take the two values that I got. You're looking over here now. I got my calcium as 0.047 and my hydroxide is 0.021. I'm going to square that, and I get a Qsp of 2.1 times 10 to the minus 5. And what I notice about that is that's a heck of a lot higher than my Ksp. This is the reaction we're looking at here. If my Qsp is higher than Ksp, the direction it needs to shift to get lower is going to be to the left. What are we cranking out on the left? Solid. Okay, so we're going to be making lots and lots of precipitate here because the equilibrium lies too far to the right to be at equilibrium. To get back to that position, it needs to shift left.